Hello everyone. Last time we saw how to find Laplace transforms using the formal definition, and now we're going to see how to use tables to make our job simpler. And I sent you an email with an attachment that has basic Laplace transforms, and this is what it looks like. This is our table that we're going to be able to use. So kind of extensive, as you can see, and at the bottom right, I actually cut and pasted some of the common series that we're going to be using toward the end of this course. And this document you could use on the final exam, which we're calling Exam 5. And so make sure you print that and keep it in a safe spot, and you could write anything that you like on the back and bring it into the final exam with you. So last time we saw the definition, and it was a little bit cumbersome because it involved, this is just flashing the notes from last time, it involved the a formal integral, okay, for the Laplace transform. And so it got a little bit tedious in terms of the integration, and you're going to have one question on the final exam, or an Exam 5, whatever you want to call it, regarding the formal definition, and it will be an exponential function like this one, so it'll be e to some power, not 3t, obviously. I'll just change that, but it will be very similar. So getting to using the table, before we discuss it, there's a couple important concepts that'll go without proof here, but we have first off what we call the gamma function. So this Greek letter that almost looks like you know what you make when you're playing hangman, is the uppercase Greek letter gamma. And so it's our gamma function, and there's the definition. Integral from 0 to infinity e to the negative t times t to the x minus 1 with respect to t. So kind of a complicated looking function. It's going to go without proof, but it can be proven that gamma of x plus 1 is x times gamma of x, and that gamma of 1 is 1, just by using this definition. And so the first thing is to get used to working with gamma. And so we've established that gamma of 1 is 0. Here's some other examples. Let's say you wanted gamma of 2. Okay, so basically you're using this definition here to begin with. And if we're looking for gamma of 2, that means x is 1. So therefore it would be 1 times gamma of 1. But then gamma of 1 is 1, so 1 times 1 is 1. Okay, let's just go up the ladder here, so to speak. Gamma of 3 would mean that x is 2. And so therefore it would be 2 times gamma of 2. But then you could use gamma of 2 is when x is 1. So that's 2 times 1 times gamma of 1. But then gamma of 1 is 1, so 2 times 1 is 2. Just do a couple more. Say gamma of 4, or gamma of 4. That means x is 3, so 3 times gamma of 2, or 3 times gamma of 3, excuse me, which is then now 3 times gamma of 3 means x is 2, so 2 times gamma of 2. But then gamma of 2 means x is 1, so 3 times 2 times 1 times gamma of 1. But then gamma of 1 is 1, so 3 times 2 times 1, or 3. And so, in general, we could say that gamma of n plus 1 is n factorial, because if you consider gamma of 4, that would mean n is 1, and I'm sorry, 3 times 2 times 1 is 6. Okay, so when gamma is 4, you would have n as 3, so that'd be 3 factorial, and that's exactly what we have here. And if you want further, I don't know, I guess I will for the fun of it. Let's say gamma of 5, just to illustrate the concept, means x is 4, so 4 times gamma of 4. But then gamma of 4 is when x is 3. So we have 4 times 3 times gamma of 3. But then gamma of 3 is when x is 2. So 4 times 3 times 2 times gamma of 2. But then gamma of 2 is when x is 1. So 4 times 3 times 2 times 1 times gamma of 1. And then gamma of 1 is 1. So 4 times 3 times 2 times 1 times 1, which is 24. So that further illustrates the concept of gamma of n plus 1 being just n factorial. Okay, and then there's a special value, gamma of 1/2, and that's the square root of pi. And that definitely is going to go without proof. I mean, if we were in class, I don't normally prove it, but at this point, we're going to leave it without proof. But if you want, I'll send you the proof. Just email me. The textbook says it's far from obvious, and that certainly is true. But besides those tools, the idea of calculating gamma and gamma of 1/2 being equal to the square root of pi. Oh, let me give another example, actually, before we go on. You're going to use this concept whenever you have to evaluate gamma of a fraction. And typically it's going to be with a denominator of 2. So first off, gamma of 5/2 means that x is 3/2. So therefore that's going to be 3/2 times gamma of 3/2. But then gamma of 3/2 in our basic definition for gamma of x plus 1 means that x is 1/2. So therefore we'd have 3/2 times 1/2 times gamma of 1/2. But then we use the fact that gamma of 1/2 is the square root of pi. So 3/2 times 1/2 times the square root of pi, or let's just say 3 square roots of pi over 4. Okay, so that is certainly something that we're going to be using as we'll see it through these examples. And then we have a special property that it's kind of, you'd almost assume that this is true. It's what we call the linearity property of Laplace transforms. If you take the Laplace of a function that's a constant times a function plus or minus a constant times a function, basically you can take the Laplace of a sum or difference, and the constant multiples are can be factored out of the Laplace transform. So that would be equal to factor out the a Laplace of the function of t, and then plus or minus factor out the b, and then the Laplace of the function of g. So the first thing we'll do here is consider the Laplace of this function, 3t to the 5th. That tells us to use a table. So we want to use a table from now on. No use using the formal definition, as we saw. It's quite cumbersome. So there's the fancy L, okay, that we typically use. And so the first move would be to use the linearization property. And so that's going to be 3 times the Laplace of t to the 5th, and then minus 2 times the Laplace of t cubed. Okay, and then at that point we can go to our table, and we're looking for t to a power, so for both cases. And if we look amongst the there's 2 columns here with their corresponding transforms. So you can see this first set, here's the function, here's its transform, And then this column, here's the function, here's its transform. And so we're looking for t to a power. And so, looking amongst the lists, okay, here's t times f of t. Here's t to the n, but times f of t. That's not what we're looking. Oh, look at it toward the bottom here. There's t to the n. Now also notice that we have t to the a. And they work out to be the same thing, but notice that t to the a involves the gamma function. So t to the n is used when n is a positive integer, and t to the a is used when a is a fraction, okay, containing a denominator of 2. And so make a distinction. You could write it on your table if you like. I'm not going to write it on this one, but make a distinction that t to the n is used when n is a positive integer, and t to the a is used when a is a fraction with a denominator of 2. So it's basically saying that the Laplace of t to the n is n factorial over s to the n plus 1. So let me write that out over here off to the side. In general, the Laplace of t to the n is n factorial over s to the n plus 1th power. Remember, I'm going to make my s's like that, because otherwise it'll look like 5s. So this is just simply 3, and then the Laplace of t to the 5th, n is 5, so 5 factorial over s to the n plus 1, so there'd be s to the 5 plus 1 is 6. And then here we have minus 2, same formula, n is 3, so 3 factorial over s to the n plus 1 is 3 plus 1, or the 4th power. And then evaluate the factorials, so that's 5 factorials, 120, use a calculator if you need to. It's just 5 times 4 times 3 times 2 times 1. So 120 times 3, so 360 over s to the 6th minus 3 factorial 6 times 2 is 12 over s to the 4th. Okay, so that's how we handle that one. For the next one, Laplace of 6 e to the 3t minus 4e to the negative 2t is going to be, so the first move is the linearity property. So 6 times the Laplace of e to the 3t minus 4 times the Laplace of e to the negative 2t. And then if we look at our table, we're looking for e to a power, and it turns out that it is in, I think, the second column here, the second set of columns. So there's e to the at, one of the most commonly encountered functions, and it's just 1 over s minus a. So let me write that down off to the side. The general transformation for e to the at is 1 over s minus a. So this would be just 6 times 1 over s minus a is 3, and then minus 4 times 1 over s minus a minus 2, so let's just more efficiently write s plus 2. And so we get 6 over s minus 3 minus 4 over s plus 2. Okay, now we get to an example that involves, well, a cosine function, but then t to the 3 halves. So the first thing is set it up, Laplace of t to the 3 halves minus 4 cosine 2t. Okay, so that's the Laplace of t to the 3 halves, and then minus 4 times the Laplace of cosine of 2t. Okay, for the Laplace of t to the 3 halves, we're going to have to use the formula for the Laplace of t to the a that I had mentioned earlier. And so that's the one that involves gamma. Gamma of a plus 1 over s to the a plus 1. It's really the same formula, but it's necessary because the power on t is a fraction. So it's gamma of a plus 1 over s to the a plus 1 power. Okay, and I might as well write down the Laplace of the cosine of function. So if we look for the cosine, they use k here. In the second set of columns, cosine of kt is s over s squared plus k squared. So Laplace of cosine of kt is equal to s over s squared plus k squared. But one thing that we're going to need is gamma of 3/2 plus 1. So I'm going to do that, make a little line here and a little line here. Okay, we're going to finish the problem off here, but I'm going to calculate gamma of 3/2 plus 1, because that's what we're going to need for t to the a, where a is 3/2. So that's gamma of 5/2. And so that's going to be, according to our formula for gamma of, so that's back up here, okay? That's the formula for gamma of x plus 1. That means x is 3/2. So therefore it's going to be 3/2 times gamma of 3/2. But then gamma of 3/2 is when x is 1/2, so it's 3/2 times 1/2 times gamma over 1/2. But then we finally use the property, the special value, that gamma of 1/2 is the square root of pi. So we get 3/2 times 1/2 times the square root of pi, which let's just write as 3 square root of pi over 4. And so therefore we have gamma of a plus 1, we just found it, 3 square roots of pi over 4, divided by s to the a plus 1. A is 3/2, so s to the 5/2. Okay, and then we have this minus 4, and the Laplace of the cosine of 2t, we're using this formula. And so that's s over s squared plus k is 2, so k squared, 2 squared, which is 4. So maybe make this 3 square root of pi over 4s to the 5/2 minus, I'll make this 4s over s squared plus 4. Okay, so move on to the next example. Got a second page of examples here. And so, first move once again. Laplace of, here we have t to the 5/2 minus 3. That's the hyperbolic sign, sometimes referred to as sinh, of 6t. So linearization, Laplace of t to the 5/2 minus, factor out the 3, Laplace of the hyperbolic sign of 6t. Okay, we already stated the formula for Laplace of t to the a. We'll do it again off to the side here. Laplace of t to the a, okay, because again we're going to need that formula because this is a fraction, the 5/2. So that's gamma of a plus 1 over s to the a plus 1. And now we're going to need the Laplace for the hyperbolic sine of, again, they use kt in the table. Okay, so obviously just want to reference your table here. For hyperbolic sine, it's k over s squared minus k squared. Okay, and then I'm going to do a little wavy line thing again, because now I have to evaluate gamma of a plus 1, where a is 5 halves. Okay, let me do a little wavy line here, and then we'll finish up the problem in this space. So that's gamma of 7 halves. And once you get used to this, you realize it's really just 7 halves, and then, excuse me, it's going to be 5 halves, because x plus 1. Once you get used to it, you could skip steps, because it's really just going to be 5 halves times 3 halves times gamma of 1 half. But we'll show it explicitly. So 5 halves, gamma of 5 halves, which is 5 halves. Gamma of 5 halves, that's when x is 3 halves. So 5 halves times 3 halves times gamma of 3 halves. And that's 5 halves times 3 halves times, now gamma of 3 halves is when x is 1 half. So 1 half times gamma of 1 half. And that's the point we want to get to, right? Gamma of 1 half is the special value, square root of pi. So let's just make this 15 square root of pi over 8. Okay, so that's going to be our numerator here. 15 square root of pi over 8 divided by let's see. Write a formula s to the a plus 1, and a is the 5 halves plus 1 would be 7 halves. So s to the 7 halves, and then we have this minus 3, and then our formula for the Laplace of the inverse of the hyperbolic sine, excuse me, of kt is k over s squared minus k squared. K is 6, so 6 over s squared minus 6 squared. And of course you could have squared the 6 right away. So 15 squared of pi, I'll write it as over 8 s to the 7 halves, and then we'll make this minus 18 over s squared minus, make sure you square that number, s squared minus 36. Okay, I think I'll stop right there for this part, because then otherwise I'm going to go well over 30 minutes, and sometimes that's an issue with YouTube. So we'll finish off this part in 10-15 minutes, and then we'll move on. So we'll see you when you're ready.